Welcome, everybody, to Florence School of Regulation online talk. Today's topic is about hydrogen. Is the hydrogen the fuel of energy transition? I believe it's a very timely discussion. Europe is really preparing in bringing forward the objectives of European Green Deal. There will be World's Hydrogen Fuel Summit in March in Amsterdam. And in Germany, government now very actively discuss proposal for Germany's national hydrogen strategy. I'm really glad that the European University Institute's Robert Schuman Center has published policy paper called Molecules, Indispensable in the Decarbonized Energy Chain by Ronnie Belmans and Pieter Vingerhoets. Ronnie Belmans is well-known name from KU Leuven, world-famous university. Pieter Vingerhoets comes from VITO, Flemish research organization, in the area of clean tech and sustainable development. I hope soon will be also extremely world-renowned name. But both of them are also working in Energy Wheel, that is a cluster or European innovation hub in energy. So that means that there is really good cooperation from different research organizations. We'll have also anticipated that later in our discussion we'll join Yves Vercammen from Fluxys. It is actual from business, also from Belgian gas infrastructure group. So it's very interesting his views on it. I will remind that we have 45 minutes for all the online talk. And that's why I would encourage you to write the questions as soon you are having them. Because we kindly agreed with Ronnie and Pieter that they will stop in some places just to answer the questions if there will be any. But now I really have the privilege to give the floor to Ronnie and Pieter. Ronnie, the floor is yours.
Thank you, Andris, for these kind words of introduction. As you say, we tried to have that paper written and to really discuss it with many people, but having the occasion in this talk to discuss it with a lot of people and to get impact via it and also input from the discussion is very timely for us. We are discussing hydrogen as if it's something new, but of course, hydrogen is known as being the lightest element on Earth. It is an odorless gas with a very high energy to mass density, but a very low energy to volume ratio. This is something we have to keep in mind very much because this is going to make one of a hell of a difference for the applications that will be seen later. It has been used for a long time in history, and I think the rocket at the right-hand side is probably the best known example of hydrogen in transport. It's a Saturn V rocket for going to the moon. But this is not what we are talking about. The hydrogen used today is about industry, chemical industry, refining industry, iron and steel, and in general industry like semiconductors, glass production. There is already an extreme big amount of hydrogen which is used today. And also in the future, in the decarbonized society, we will need those applications to be supplied with hydrogen, but then with green hydrogen. And as Andris said in his introduction, hydrogen is gaining momentum, and a lot of momentum and a lot of interest in the press. And when seeing that, we have been wondering ourselves, why is all that attention there, and what are the physical pros and cons of hydrogen and other molecules in the system? Can we have a fully decarbonized system without molecules? And if not, which molecules do we need for what applications? The first part is, how do we produce hydrogen? As I said, it's already used for a long time, and it's used a lot. So the question is, where does it come from? And it comes from gray hydrogen, steam methane reforming, from natural gas, from methane. Or a lot of it is also black, specifically in Australia, very popular, where it comes from coal. Another portion is blue hydrogen, which is in fact the same as gray hydrogen, but the installation is then equipped with carbon capture and storage, or carbon capture and use. And then we have electrolysis, being green hydrogen, if all the electricity that is supplied to the electrolyzer is coming from the real green electricity. Of course, if part of it comes from other resources, there is some CO2 involved. And that is one of the major things we have to look at. How green is the electricity that is supplied to the electrolyzers? And that's a very much important part of the game if we're talking about taxonomy of the whole hydrogen community. If we are green hydrogen and the electrolyzers, we are coming in a very interesting situation. So we produce from water, clean water, very clean water, plus electrical energy, we produce hydrogen, oxygen, and some heat. By the way, ladies and gentlemen, it's very interesting to see that there is also such a thing which is not in the paper called pink hydrogen, which is hydrogen that is supplied from nuclear reactors as a way to go to hydrogen directly. It has got some attention 1 or 2 decades ago, just for completeness. But the question is, if we make hydrogen from electrolysis, how green is this hydrogen? This hydrogen is normally formed by steam methane reforming, and if you do the calculation, you get 7 to 9 kilograms of CO2 per kilogram hydrogen. This is, of course, the normal thing. This is how it is done today. So this is the basic figure, and we have to do better to improve the CO2 output and to go to decarbonization. If we have the electrolyzing coming from fully renewable energy, you get, of course, 0 gram of CO2 per kilogram hydrogen. But if we go from electricity directly coming from the EU mix, you have part of it coming from 0 carbon-based renewable energy, 0 carbon-based nuclear energy, and then you have the gas-fired power plants and coal-fired power plants, and you get to an average of roughly 16 kilograms of CO2 per kilogram hydrogen. So we have to be very careful that if we use current electricity to produce hydrogen, we do much worse than just by using classical steam methane reforming. Double amount of CO2 output if we use that mixture as coming out from Europe now. Of course, we're going to decarbonize more and more what is the electricity supply. Currently, there are less than 100 hours per year with negative prices in most member states in Europe. At the other hand, electrolyzers need a minimum of 4,000 to 5,000 hours of operation per year to be cost effective. So we have to be very, very careful if we're talking about green hydrogen today, because the green hydrogen is, even if it's as a contract supplied from green supply, say from an offshore wind farm, if that electricity is used at that moment to produce hydrogen, other power plants will be started in the grid to supply the missing electricity. So really, we have to look at the overall energy system to assess the content of CO2 of electrically produced hydrogen. And this is really the very major thing we have to look at to see that we are not increasing the CO2 output of the overall European system by locally producing green hydrogen. So this is a part we have to be very careful of. So that is, I think, the most important conclusion that we have now from how do we get to hydrogen and what are the different resources. I think, Chairman, that we have said that we should stop here and hand over to Pieter, but if there are urgent questions, please let them come.
Questions as soon as you get them, because it's easier to really to address them. But not having the questions, I will ask now Pieter to continue the presentation. Pieter, please.
Thank you, Mr. Chairman. in the second part, we will have a look in where in the energy system, which applications do we need hydrogen or gaseous or liquid molecules in any form. As you know, electrification is a very important part of decarbonizing, but it has its limits. Sorry, I'm trying to go to the next slide. Yes. So we will go one by one to buildings, transport, industry. But if you look and you see in the press projects with hydrogen, you often see the explanation: we will consume excess electricity in the grid, and when there's a shortage on renewable energy, when there's low wind and solar, we will re-electrify and will produce electricity. Now, in the paper, we did the exercise of looking at the efficiencies. Suppose you are in a warm, sunny country, and you would produce renewable electricity, for example, by concentrated solar power there, and you would import it into your end consumer in your country. If you use an HVDC link, of course, not too far, you would get around 79% efficiency. And this is by all means a conservative figure, because this includes the losses not only for the HVDC link, but any possible losses you would have in the medium voltage or distribution grid. If you convert locally to hydrogen, you ship the hydrogen, and there locally you re-electrify, then you have an efficiency of around 25%. And a lot of energy is lost with the liquefaction of hydrogen and the transport. If you convert locally to synthetic methane, you have 32% efficiency. The disadvantage of converting to methane is of course that you need a CO2 source. So if you look at these efficiencies in the system, there's a few messages here. To the right, we also list a few applications and their efficiencies compared to the electric pathway. And I think the message is one: if you have electricity and you can use it directly, you should try to use it directly. And secondly, if the only purpose of the hydrogen is re-electrification afterwards, there are other technologies that can contribute to that. You have increased flexibility, you have increased interconnections, you have power to heat storage, for instance. So don't forget, don't focus only on this one energy carrier, and look at the entire energy system, including the different technologies. What is a very key advantage of molecules in terms of storage is that you can store molecules for quite a long time. Within the day, you can do a lot with batteries, but they're not suitable for multi-day to week storage. And then beyond that, for real Dunkelflaute, their molecules as strategic storage, they will be very useful. Secondly, we look at hydrogen or molecules in buildings. Well, in the built environment, there's strictly no need for molecules. There are solutions like heat pumps, district heating on high or low temperature, where you can also valorize excess heat or waste heat that is produced in the system. And similarly to what we've seen before, you have also the efficiency issues of hydrogen heating compared to a heat pump is at least 3 times less efficient. We will not go in detail to the safety issues, but of course, transporting a flammable gas, it comes with also a set of safety issues. It is technically, of course, feasible, but there are some different requirements with respect to methane. Where you do need molecules in the built environment for heating is for certain special types of buildings, like hospitals, for instance, that need liquid backup generators that often are powered with liquid molecules. And also in remote places, you might have molecules as a backup. Then storage. In this picture, we provided an illustration of the energy to volume ratio of certain technologies. For person transport, we see that electrification is already ongoing on a quite massive scale. For long distance transport and more heavy transport, electrification will most probably not be sufficient due to the low energy to mass ratio and energy to volume ratio. We compared here with a few other carriers. You have the gaseous forms of hydrogen, the different pressures, and if you compare, you see that the volumetric energy density of liquid fuels is here the highest. So what can we conclude? Of course, in all this, the efficiencies are a hint, but the system cost will be the determining factor. But for transport, certainly for person transport, also the missing infrastructure for hydrogen fuel stations will be an issue. So we see in summary that for short-term and short-distance persons transport, like local buses, bikes, electric bikes, electric cars, that electricity will probably be the most interesting, also because an electromotor is almost 3 times more efficient. For long-distance transport or more heavy transport, you will need molecules. We're talking about shipping, intercontinental shipping. Which type of molecule is not sure yet, but for airplanes, that is for sure, you will need a liquid form of molecules. Then, at this point, you might think these guys are not enthusiastic about hydrogen at all, because we've seen for electrification, there are competing technologies for transport, only for the long distance transport, and for a built environment can also do without hydrogen. But don't make any mistake, the quantities required in industry, they are huge. And a very large amount of hydrogen is already required today and will continue to be required in the future, especially, as Ronnie mentioned, in the industry, in the chemical industry, for instance, ammonia production. In the steel industry, I think the jury is out. You see some activities towards direct reduction of hydrogen, but there are also other technologies based on capturing CO2 and reusing CO2 or creating bioethanol, for example. So in summary, I think in the industry, the main message here is if you do want to create hydrogen, the main and the most sure and the most valuable application will be in industry. And secondly, to a lesser extent, in less quantities, but not unimportantly, molecules will be needed as a backup for strategic energy storage. So I think we were asked to stop here if there were any burning questions.
From Manuel Villavicencio about the different shades of hydrogen, basically CO2 footprint. Ronnie answered to the question that in publication there was not so much differences made. But if I may just a bit rephrase the question for Ronnie. Ronnie, do you think it's helpful to separate hydrogen like gray, black, green, blue, or it would be just, well, the hydrogen that has no emissions of greenhouse gases involved, and that's it? Because now with the sources, it's rather popular, but does it help, or in your opinion, doesn't matter too much?
I think, do you hear me? I think
Yes,
you do? Yeah, okay. I think, moderator, it's a very important question. And I think we should really take very much care, maybe not about a 1 or 2 or 5% with CO2 between very good blue and almost perfect green electricity. But I think we should be very careful that we really put forward the real CO2 content of the whole product. because greening hydrogen, like greening electricity, like it was done in the beginning, and we have to be very sure it was also done with green electricity in the beginning, with biomass and mixing biomass and co-firing biomass and using waste and bio-waste for producing green electricity, has done an awful lot of harm at that moment. So we have to convince the public that it's really green. Otherwise, it's not going to really contribute to the full decarbonization. So I would plead a lot from the beginning, not redo the mistakes that we did in the beginning with electricity of partially greening and almost greening, that we do it correctly from the beginning. We have to learn our lessons. There are enough mistakes to make that we don't have to do the same mistake twice.
He asked, is the use of hydrogen in industry only needed as a feedstock and not as an energy vector? If so, how could it contribute to decarbonization of those sectors?
So I think in the industrial sector, you will also see some electrification for processes which require heat, for example, this Gemmelot project where there will be naphtha cracker electrification. So electric installation for naphtha cracking. But of course, hydrogen might be there also as an energy vector for producing heat. And to this extent, what will be exactly the capex installations in which type of processes, this requires a more detailed study, and this is a little bit beyond the scope of the paper.
I think, Chairman, that it's very difficult sometimes to see what is the energy vector or feedstock, because hydrogen can first deliver energy and then be part of the molecule that is produced. So when does it start to be part of the feedstock, and when is it an energy source? This is very difficult, and that's typical about that whole interaction in industry. But it is needed, period. And whether it supplies energy as part of his job is probably an academic discussion at that moment.
Yeah, Ronnie, perhaps now let's conclude the presentation of paper. And I have some other questions that I will come after your concluding.
Okay, so it's going to be a key molecule, but is hydrogen the basic molecule? And then you have to look very carefully to that table, and you see the pro and cons. And the pro and cons especially is the energy density per volume, which is for hydrogen the real bottleneck to do things. And that's why for transport applications, like we said, for shipping and for flying, that probably liquid molecules, or liquid molecules, that means also methane at reasonable liquefaction temperature of minus 160 degrees, is probably the way to go. But of course, hydrogen in the production of all those molecules will be key. And you see this on this drawing. You see at the left-hand side all the input to produce hydrogen, and you see the green and blue hydrogen coming out of it with CO2, and you see how that hydrogen is at the kernel point of all the decarbonization for all the molecules, being molecules for chemistry and transport, or going to the steel and chemical industry. So hydrogen is a focal point, but will not be seen that much by the end consumer. And that's the main message, is hydrogen in the decarbonization process of our society is key. But at the end, we will see an awful lot of applications where hydrogen is not presented at the final consumer, but is embedded in products, in chemistry, in molecules for energy supply and for energy services. Mr. Moderator, that's it.
About natural hydrogen resources, we have any quantification of the amount of the stock? I would perhaps rephrase it. Does the amount of hydrogen that we can produce depends on the amount of water that we have on the planet, or there are other limitations in it? And another question is related to greenness on carbon emissions from electrolysis. Is only the origin of electricity important, or are there any other factors. And then there is also a question about different costs in producing various shades of hydrogen. Do you see the cost of hydrogen being driven by electricity price? Here I stop because we would need also to get the
I will pick up a few of them, and Pieter can also pick up a few of them, but we limit ourselves to a minute or two. Of course, there is water needed, and a lot of that green electricity is available at places where water is scarce. If you look at desert type environment, if you need water there as a basic product to produce your hydrogen, this might be a challenge. Okay, we have to be very careful how it is done. You also need to, for desalination, if you use it at a coast site, if you take salted water, that is going to be a challenge too, which has to be part of the equation. But as I said, this is the first paper where we try to bring in the most of the ideas together. You must know that Pieter is leading a new project called Procura, where they will try to make in 4 years with roughly 10 PhD students and researchers to make a good model for doing this whole thing. So it's not so easy to make it in one paper with two brains sitting together here to make the full picture. Talking about the whole thing about the electricity price, hydrogen, if the electricity price of a surplus of green energy, of green electricity, is by definition zero if you're taking the marginal cost. So if you have other resources needed, then you have to be very careful, because most of the non-marginal cost electricity resources are carbon-based. So that's a reasoning why I would say the electricity price, if it's used for the whole thing like producing hydrogen, will be not the problem, because it won't be there at that moment. But it is still in much of research to be done. Pieter, final comment?
I've seen this question from Bram. I think we can, if you can clarify, Bram, what you mean, because the carbon emission of hydrogen from electrolysis depends, of course, on the electricity used. I don't exactly know what you mean by feedstock, because propane dehydrogenation and creating propylene is then the application of hydrogen. So I think we can take it along to the discussion. How does the work of Johan Martens of the KU Leuven fit in? Well, it's a different way of producing hydrogen directly with solar panels, and it can be useful. It's a different way of producing this hydrogen, and I think what will be exactly the technology that provides the services needed for industry, I think we'll have to see, and innovation is certainly needed. This is a point we have not mentioned yet. On all parts, innovation is needed to explore the technological boundaries.
A couple of words about policy paper by Ronnie and Pieter. You are also welcome. Yves,
yes, good afternoon to all of you. I think there was just 10 more minutes left, so I would very quickly like to guide you through one of the key considerations that are often used when talking about hydrogen. That is, it was already mentioned by Pieter and Ronnie as well. How can hydrogen play a role in a decarbonized energy system? And I just would like to give you some food for thought. We don't have a lot of time to debate into too much detail, but just if we think about a renewable system, and I'm trying to move the slide forward. Yep. When we talk about the renewable energy system, we talk about a lot of sun and wind energy, and we all know that these sources of electricity are intermittent, and hence you end up with profiles like the one that is being shown in the graph below. This is just a snapshot of the electricity provided through wind farms into Belgium. So we're talking about a relatively small amount of gigawatts being produced. And you might have remembered that a couple of weeks ago, there was in Northwest Europe a kind of period of 3-4 days with almost no wind. And as a consequence, per definition, if the wind isn't there, there is no electricity from the wind neither, and you end up with reduction of available electricity. And if you want to compensate in a decarbonized energy system this flexibility, you need to have tools. And nowadays, the tools that are mostly always mentioned are, we are using batteries, we will be using demand-side management, and we will make sure that we can cope with these changes in demand and supply without any problem. Just to give an indication, the biggest battery that is today operating is the one that was built in Australia by Tesla. And if you were to put, and you see the numbers on the slide, 20 of these battery parks next to each other, you would be able to have a capacity of 2 gigawatt available for 78 minutes. So just to say that the magnitude of the problem coming from the intermittency of renewable energy is quite big, and hydrogen as such can play a role in that. And the way that you should look at it is not to look at the needs in electricity or the needs in gas or anything else as such. You need to look at it from an energy system point of view. And you need to understand that at the end of the day, a decarbonized energy system will be consisting of different elements. And of course, today, natural gas is a key component of the energy system, but natural gas is a fossil fuel. So if you want to end up with a decarbonized energy system, you need to decarbonize the fossil fuels. And hence, the objective of having hydrogen into the energy system as being a part of the required structure is key, next to other elements, because we will still be needing some flexibility, a lot of flexibility tools like demand-side management and so on to cover with the short-term and long-term flexibility that I just mentioned. So at the end of the day, how does then come this renewable hydrogen into play? It has been discussed by Pieter and Ronnie. Through power to gas, you can indeed convert electricity into molecules. And these molecules you can store and reuse at a later stage, again, when it does make sense from a system point of view. Not just for the sake of converting electricity in molecules and converting back into electrons. It doesn't make any sense. It has to be done because at the system level, this is adding value or limiting the costs if we were to do it differently. And then also a very important element about hydrogen is that hydrogen as such, it was already mentioned as well, is a kind of building block that allows to further build other renewable products, whether it is synthetic methane, for instance, by capturing CO2. If you have synthetic methane, you can, of course, reuse the existing infrastructure without any problem, which from a societal point of view can also make sense to make the energy transition affordable, which is, I think, a key element to take into account as well. Besides that, you can also convert the hydrogen into other molecules that are useful for the industry and where difficult to abate sectors can use this type of renewable molecules to get the CO2 down or even up to zero. So at the end of the day, the message is that in an energy system, we shouldn't be looking at just electricity, but we should be looking at all the energy needs as such. And the way that power to gas can operate is, in fact, helping to cope with the flexibility that I mentioned already at the beginning, which is a short-term flexibility. But we all know that the flexibility, if we combine heat demands, is even much bigger than the pure electricity flexibility as such. In the winter, we need much more heat than in summer. And hence, you have, if you look at the entire energy system, much more needs during the winter periods than during the summer periods. Thanks to this power to gas technology, you can indeed foresee that at certain point in times when the production is much higher than the offtake, you convert that excess electricity into molecules that then again, as I said, you can use later on to cope with potential shortages or to meet with the flexibility demands. Some might say this is indeed nice, but very conceptual and not yet relevant. If we look at Germany, already today, given the high penetration of renewables, there is from time to time a request to the wind farm producers not to produce any electricity from wind farms because there is or a mismatch with the demand or there is congestion, which is also an element that at the end of the day can be discussed. But in this case, you see that, for instance, last year in Germany, about 10 terawatt hours of energy was being curtailed, energy that could have been used for producing molecules and be reused at a later point in time. Another benefit of this element is indeed the fact that we will be needing different type of flexibilities, different type of storages, and the chart is showing that for each type of flexibility, we'll have the adequate type of flexibility infrastructure to help meeting these demands. And it is clear that molecules are a way to provide long-term, what we call seasonal storage. And hence, if these molecules are decarbonized, then at the end of the day, you end up with a kind of system whereby you end up providing this flexibility by using, to a large extent, existing infrastructure. And what is showing on the slide as well to the right is the fact that you can end up using today's technologies with a way to provide flexibility to the system without releasing any CO2, by capturing the CO2, by creating synthetic methane and so on, which is a concept that at the end of the day could be put in place without too much concerns from a technical point of view. There are, of course, lots of concerns from a cost point of view. But then again, the only way to look at this type of analysis is to look at it from an energy system point of view, and not just from a purely isolated commodity price point of view. To quickly finish, because I think I'm running out of time, I think we all starting to understand that if we want to have a decarbonized world, or let's say a decarbonized Europe, it will be quite difficult to foresee on our own needs, in our own needs at European level. So highly likely we will have to be able to accommodate the import of renewable energy from places where there is indeed a possibility to produce cheap hydrogen. And so as a company, we are looking into possibilities to receive all these type of hydrogen carriers on one hand through the terminals, or we are participating to projects whereby we are looking in the construction of big backbones that would allow to bring hydrogen from places where there's lots of wind or lots of sun through this infrastructure to the places of production. So in order to really have hydrogen becoming a reference in the future energy system, for sure it will have to be done at a very cheap way, and hence production areas where this can be done should be taken into account. And to wrap it up, more or less, other projects where we are participating as well. The slide is not moving. So first of all, there are lots of power to gas projects all over the world, more and more. There is a website, and you can see the link to the website where you can find all these projects. So it's very interesting to just take a look at the link. One of the projects that we are developing as a company is a project whereby we would like to build a 25 megawatt electrolyzer using the renewable electricity from offshore. And so hopefully we will end up with a FID for this project in the coming months. Another interesting project is the one that is mentioned as well in Germany, where this concept of reusing hydrogen for different needs is really being analyzed, whereby electricity will be used to convert electrons into molecules. The hydrogen is then used to create synthetic fuel that is then used by the airport nearby. And the CO2 is captured from a cement factory that isn't far away from the electrolyzer neither. So the ecosystem idea is something that more and more will pop up as well, whereby industries will join in order to make sure that they can or minimize their own footprints and or maximize the reusability of the different vectors that are around. So I'm going to stop here to give also the room for questions.
I would like to put two questions, one to Ronnie, one to Pieter, that we got from our participants. To Ronnie, Yves also mentioned it, how to get cheap hydrogen and green hydrogen, cheap and green, yeah. And for Pieter, if we have such a clear understanding about end uses, should not be trying to put the whole system top down? It's Stefano's question in a way, because then you have like a plan. It's like Netherlands transition from coal to natural gas. shouldn't we go this way in Europe? So who are you?
I think, Andris, and I think that Yves also pointed to it, the hydrogen that we need to produce all the molecules that we need to decarbonize the full system, to produce that in Europe and its direct surroundings will be extremely difficult and certainly not economic. If you look at a big space that you might need to do that, then you see that we end up to produce that hydrogen and then the molecules directly there or whatever happened in regions where there is a combination of good wind and good sun. And often this is the coastline of sandy landscapes, which happens to be at a place that at this moment is also a lot of those carbon-based fuels. And whether it's going to be less expensive than those carbon-based fuels are today, probably not. But we don't account for the CO2 output and the cost of that at the moment. So it's not going to be a cheap thing, but if we want to do it, it will be there. And then, of course, you come back to the whole problematic that we have now is strategic storage of fuels. But I think that Yves can there tell much more than I can. Yves?
So it's a very difficult question to answer in the sense that at the end of the day, as I said, and you confirmed, this will only work if it is affordable. Hence, we need to find the cheapest way to produce hydrogen as such. The concept of strategic reserve is a concept that at the end of the day also will need to be taken into account. And then I come back to the flexibility debate, because the strategic reserve is to some extent there to cope with flexibility demands that might arise if you look at oil because of a kind of rupture, of disruption. Whereas if you look at the gas and electricity sector, it's just to cope with the flexibility demands. If we are to look into the overall energy system, we will have to take into account that somehow this flexibility will have to be met with. And then the only way that you can do it is to organize it completely decentrally or completely centrally or something in between. So at the end of the day, I think the answer will become visible along the way. It will be a combination of different approaches.
So I think it's a very interesting question. Should we define the pathway top-down? I think at least to some extent you need to let the market find its own solutions. However, there's still important challenge for regulation as well. And as Ronnie already mentioned in the chat box, very important is to have a taxonomy and to take care of the CO2 accounting in all the processes in the energy system. And I think the main challenge here is we need a combination of regulatory incentives and solutions found by market players. And I think it's very important that you are aware that you are beware of sunk costs and infrastructure investments. For example, if I compare Ostend communication to what Rotterdam is communication in terms of which options are there for clean molecules. You see on the one hand hydrogen, hydrogen, hydrogen. On the other hand, you see hydrogen, but also possibly methanol, also possibly ammonium, and we keep the options open there. So I think very important in this process is first carbon accounting, and secondly keeping infrastructure options open.
Thank you, Pieter. There are more questions, but I would like again to thank Ronnie, Pieter, and Yves for the presentations being made, for their willingness to answer the questions. Ronnie sent 2 emails by Pieter and Ronnie, so you could ask any more questions to Ronnie and Pieter, and they will be also kind enough to pass the questions to Yves. So if you have some questions to Yves, I would like to thank my colleagues that repaired the link to the publication. Now everybody has an access to this publication. And also I would like to thank Chiara that managed all the operations that we have had today. So thank you very much for all your participation, and I invite you to the next Florence School of Regulation online talks.
Bye-bye.